Welcome to the Deep Dive, where we take the complicated and, well, try to pull out the essential insights for you.
That's the goal.
Today, we're diving deep, really deep, into the absolute bedrock of artificial intelligence development. We're going to step back from the flashy headlines about the newest large language models for a moment.
Right. Set those aside.
And really focus on the underlying mechanics. Specifically, 3 pillars. Foundational pillars that dictate whether an AI model is truly intelligent, truly generalized, or if it's just a clever trick.
And those are?
Ground truth, the strategic need for semi-supervised learning SSL, and the mathematical engine driving it all, loss function.
That's exactly right. Look, for anyone out there evaluating AI reliability or maybe trying to optimize a machine learning pipeline, this deep dive, it's basically your manual for understanding how quality is actually achieved. Our mission today really is to move past just the simple definitions of supervised learning. We want to give you the granular mechanics, the deep understanding of data strategy and feedback loops. That's what separates the high-performing models from the ones that just, well, fail in the real world.
We are definitely unpacking the crucial difference between building a model, one that works okay on your test data,
Right.
and building a reliable, generalized model, one that works everywhere. You can build a system that hits 99% accuracy on your neat little training data set.
Happens all the time.
But if it immediately crashes and burns when it sees new real-world information, then you've built something brittle.
Exactly. Brittle is the word.
And that reliability, it starts right here. Section 1.
Yeah.
The absolute foundation. Establishing ground truth.
Okay, ground truth. At its core, you need to think of this as the verified, true, unassailable data. It is the objective reality your model has to learn to replicate.
Objective reality. I like that.
Think of it like the constitutional law for your AI system. It's the benchmark. Everything gets measured against it. Every prediction, every learning step, every final performance metric.
So if it's wrong...
If your ground truth isn't impeccable, you're basically teaching your AI system a fundamental lie from the very beginning.
Okay, so in supervised learning specifically, this means the data's been rigorously annotated, right?
Yeah.
Labeled.
Precisely. Labeled. So if the task is classification, say, identifying objects in an image, the ground truth isn't just the picture itself.
No.
No, it's the image plus the correct labels, the defining features. If we're training a model to spot a cat.
The classic example.
It always is. But the ground truth involves, precise bounding boxes, maybe even pixel-by-pixel segmentation, accurate labels pointing out cat's eyes, cat's ears, whiskers, that level of detail.
Got it.
And it's these precise annotations that teach the algorithms how to find similar patterns in new data it hasn't seen before.
Which brings us to the criticality of accuracy.
Oh, absolutely critical. If a human annotator, maybe they're tired, maybe the guidelines weren't clear, mistakenly labels a dog's paw as a cat's paw.
Whoops.
Yeah, big the model internalizes that error. It learns an incorrect connection between that visual pattern and the label cat's paw, and that guarantees false predictions down the line. It's baked in.
So what you're saying is the ultimate performance ceiling of your AI model, it's strictly limited by the quality of your ground truth.
That's the hard limit.
You could have the most advanced hardware, the most complex neural network architecture imaginable. But if that foundational data is flawed...
You're building an advanced system on quicksand, it'll look good for a bit, then collapse.
Okay, but getting that quality isn't just luck, right? It can't be accidental. It has to be strategic.
Exactly. It has to be strategic. And that's where the data strategy really comes in. Our sources, they emphasize 3 essential strategic measures that data science teams absolutely must implement for high-quality ground truth.
Okay, first one.
First is nailing the clear goal definition. Now, this might sound a bit like project management fluff.
A little bit, yeah.
But it's critical because it determines the scope of your labeling effort. You have to ensure the ground truth truly reflects the real-world operational environment the model will actually face.
Okay, give me an example.
All right, say your model needs to interpret traffic lights. Maybe it's for an autonomous vehicle system intended to work globally.
Okay.
You absolutely cannot rely solely on data collected under perfect, clear, sunny California skies.
Right, because that's not the real world everywhere.
Not even close. If the model's objective, its goal, requires it to correctly classify traffic lights during heavy fog or torrential rain or deep snow, well, then the training data must contain high-quality, accurately labeled examples from those exact difficult conditions.
And if you fail to define that goal properly up front...
Then the model might hit an initial accuracy target in your clean test set, sure. but it will instantly fail when you deploy it somewhere with variable weather. The goal wasn't matched by the data.
Makes sense. Okay, what's number 2?
Second, you need a standardized labeling strategy. This means consistent, defined schemas, rigorous guidelines for annotation, and crucially, they need to apply across all annotators in all development phases.
Ah, consistency.
Paramount. You mentioned bounding boxes for cats earlier.
Yeah.
Okay, what if one annotator draws the box tightly around just the fur, but another includes the cat's shadow in the box?
I see. The model gets mixed signals.
Exactly. It receives mixed signals about what actually defines cat in an image. That inconsistency just introduces noise, makes it impossible for the model to lock onto a single reliable pattern.
So how do you enforce that consistency?
Often through things like implementing consensus mechanisms. You might require 2 or 3 annotators to agree on a label before it's accepted, especially for trickier subjective tasks.
Okay. And the third strategic measure?
Third is dynamic data management. Ground truth isn't a static thing you create once and forget about.
It's not a finished product.
Not at all. It's a living asset. Look, the world changes constantly, right? Data distributions shift. Think about building a model to recognize, say, clothing styles. Fashion evolves fast.
Very true.
So data scientists have to continuously validate the model's predictions against new incoming real-world data. And crucially, they need to update the labeled data set whenever new scenarios, new variations, new styles appear. If your model starts making consistent mistakes on a new type of input,
You need to label that new input and feed it back in.
exactly, you incorporate it back into the ground truth to keep it current and relevant.
Okay, strategy sounds good on paper. But moving from strategy to the real world, that's where the challenges hit.
Oh yeah, they run headlong into practical challenges. The first big one, ambiguity.
Ambiguity.
Many complex labeling tasks require subjective human judgment and human judgment. It's notoriously inconsistent.
Like sentiment analysis. I remember we had talked about the phrase, good for you.
Perfect example. Without hearing the tone of voice, how does a human label that? Is it sincere congratulations? Or is it biting sarcasm?
Yeah, impossible to tell sometimes just from text.
Right. So if your ground truth is built using labels from different annotators who interpret that phrase differently, well, the model's fundamental definition of positive or negative sentiment just gets muddled. It ends up learning contradictory lessons.
And that ambiguity probably gets worse with more complex tasks.
Absolutely. It's compounded by complexity. When tasks demand specialized domain knowledge, think analyzing medical imaging, or maybe highly technical financial records, or even specialized scientific data like gene sequencing or protein classification.
Stuff where you need a PhD just to understand the input.
Pretty much, you need deeply specialized annotators for those. And these experts, they're scarce, they're expensive. That high barrier to entry for accurate labeling drastically increases the difficulty, the time, and the cost of getting consistent ground truth.
And it also makes it hard to scale up quickly, I imagine.
Exactly. You can't just hire 1,000 general-purpose annotators off the street to handle a specialized medical image dataset. You need, maybe, 10 actual medical experts, and they work carefully, which means slowly.
Okay. Ambiguity, complexity, what else?
The final critical challenge here is skewed data. This is a tricky one. It's when your labels are perfectly accurate.
So the quality is good.
The quality per label is good, but the data set itself isn't truly representative of the real world. It gives the model an unbalanced view.
How so?
Think about developing an AI for, say, credit card fraud detection. In the real world, maybe 99.9% of transactions are legitimate.
Right, fraud is rare.
Very rare. So if your labeled data set reflects that reality, the model learns a massive amount about legitimate transactions. It sees them constantly, but it sees fraudulent activity so infrequently.
That it never really learns to spot it properly.
Exactly. It can never develop robust, generalized pattern recognition for that critical 0.1% of fraud cases.
Right.
The model becomes brilliant at predicting the majority class, legitimate, but totally blind to the minority class, fraudulent. It was actually designed to identify.
Wow. Okay, so ground truth. Indispensable for accuracy, but getting it right at scale is incredibly expensive, slow, and really constrained by human limitations, especially in specialized areas.
You've nailed it.
That really sets the stage perfectly for our next section, doesn't it? The strategic solution to this data scarcity problem. Okay, let's unpack this resource constraint issue more. Pure supervised learning, SL and Rebel.
It's powerful.
No doubt. But it demands these enormous, all-encompassing labeled data sets to really work well.
Ideally.
But like we just established, manual annotation, it's a massive drain, time, money, expertise.
Yeah.
It's just hard.
And think about the varying cost of annotation, too. Simple classification, like cat versus dog, relatively cheap per label.
Yeah.
But what about high-resolution image segmentation, where you need pixel-precise masking? The cost and the time just skyrocket.
Exponentially.
Pretty much.
Okay.
And then when you move into those highly specialized tasks we mentioned, identifying specific genetic markers in gene sequencing data, maybe? Or distinguishing really subtle features in specialized medical scans, the effort needed just to get a reliable label set becomes astronomical, almost prohibitive sometimes.
Okay, so this scarcity, this difficulty in getting enough high-quality labeled data,
Yeah.
it leads directly to the data scientist's big nightmare, right? Overfitting.
Overfitting, yes. This happens when the model performs, well, almost too perfectly on the small labeled training data it saw.
Too perfectly.
Yeah, it's essentially memorized the training set, including all the noise, all the irrelevant background details, everything. But because it just memorized, it utterly fails to generalize that knowledge when you show it new, unseen data from the real world.
It mistakes noise for the actual signal it should be learning.
Precisely. Let's go back to that illustrative example, the cats and dogs one. If your small labeled training set just happens, by pure coincidence, to show all the cat images taken indoors and all the dog images taken outdoors.
Right, just random chance in a small data set.
Exactly. The model doesn't necessarily learn cat features versus dog features. It might incorrectly learn that the background indoor versus outdoor is the main defining feature.
Ah, I see where this is going.
So when that overfitted model sees a brand new image, something perfectly normal like a cat sitting outside in the garden.
It classifies it as a dog.
Because outdoor means dog in its limited, memorized worldview, it learned an irrelevant correlation because the labeled dataset was just too small, too biased to represent the full complex reality.
So overfitting basically means the model is brilliant at one tiny specific task, recognizing those specific images it was trained on.
Mm-hmm.
And completely useless for the broader objective it was actually built for.
You got it. Brilliant, but brittle.
So the strategic answer. How do we reduce this crippling overfitting and simultaneously get around the huge cost barrier of manual annotation?
That leads us directly to semi-supervised learning, or SSL. This is where we get smart about maximizing the utility of that scarce resource, the labeled data.
Okay.
SSL starts by recognizing a crucial dichotomy. Labeled data, our ground truth, is scarce and expensive. But unlabeled data, raw data, it's often abundant and cheap. Think of all the unlabeled images on the internet or raw sensor logs.
Vast amounts.
Exactly. So SSL strategically leverages a small set of those expensive, high-quality labeled examples, our ground truth anchor, and then it incorporates a much, much larger volume of that raw unlabeled data into the training process somehow.
Well, let's say we managed to get 100 perfectly labeled examples, which is hard work.
Right.
But we also happen to have 1,000 related unlabeled examples just sitting on a server somewhere, instead of just ignoring those 1,000.
SSL finds a way to use them, to extract some value from them.
How does that help?
Well, it drastically enlarges the effective training dataset. The model gets exposed to much broader contextual variety from those 1,000 unlabeled examples. It might see cats in all sorts of different settings, dogs of various breeds it didn't see in the labeled set, different lighting conditions, you name it.
So that extra exposure helps it generalize better.
Significantly. It helps it identify patterns that are truly inherent to the object, like catness, rather than just patterns related to the specific, limited context found in that small, potentially biased, expensive labeled set.
So the key advantage here is really efficiency.
Huge efficiency gain. SSL lets us draw maximum value from our limited ground truth set while using the cheap, abundant, unlabeled data to boost the model's generalization power. It helps prevent that critical overfitting failure, all without needing another massive, costly human annotation project.
Okay, that makes a lot of sense strategically. But how does it actually work? How does the model learn from data that doesn't have the answers attached? Right, understanding why we need SSL is one thing, but the mechanics, that's where the real insights are, I think. How does the model actually pull learning signals out of data that lacks that human verification?
Good question. And what's important to remember up front is that these SSL techniques, they're often not mutually exclusive. Data science teams frequently combine them, letting them work synergistically for better performance.
Okay, so what's the first method?
Let's start with maybe the most straightforward approach conceptually, the wrapper method, which is commonly known as pseudo-labeling.
Pseudo-labeling.
This
Okay.
is basically the model attempting to teach itself.
Self-teaching. How does that iteration work? Walk us through it.
Okay, step one. You train a base model only on your small, original, human-verified ground truth dataset. This model won't be perfect, obviously, but it has some idea, a starting point of known accuracy.
Got it. Partially trained.
Step two. You take this partially trained model and use it to generate predictions or pseudo-labels for that entire massive pool of unlabeled data you have.
So it's making its best educated guess on all the cheap data. Like, I'm 85% sure this is a dog.
Exactly like that. But, and this is crucial, we can't just trust all those guesses blindly. Which brings us to step three, implementing a confidence threshold.
Quality check.
Precisely. We only select the predictions where the model shows high confidence. Say, we set a threshold of 95%. Only predictions above that level, 95% certain this is a dog, are selected and temporarily treated as if they were true ground truth labels.
And the low confidence ones, the 55% guesses.
Discarded for now, or maybe saved for a human to look at later via active learning, which we'll get to. But for pseudo-labeling, you only take the confident words.
That threshold feels like the key safety mechanism, doesn't it?
Yeah.
It stops the model from just reinforcing its own potentially bad early biases.
It's absolutely the protection mechanism. If the model learned some poor initial habits, we definitely don't want to amplify those by trusting shaky pseudo-labels. Okay, step four. The model retrains, but this time it trains on a new, much larger combined data set.
The original human labels plus those high-confidence pseudo-labels.
Correct. And this whole cycle can be iterative. You can repeat it. As the model improves with each cycle of retraining, the quality of the pseudo-labels it generates should also improve, hopefully refining the overall system further.
Okay, but I can see a potential risk here. What if the model makes a consistent, systematic mistake right from the start based on a flaw in that initial small labeled set?
Right.
Like maybe it consistently mistakes a specific angle of a cat's ears for a fox's ears just because of how the initial data looked? And what if it assigns a high-confidence pseudo-label based on that initial mistake?
Then it's essentially amplifying its own flaw across the entire data set.
Yeah.
That's the critical vulnerability of pseudo-labeling. Confirmation bias. If the initial ground truth had a hidden flaw or bias, pseudo-labeling can unfortunately solidify and spread that flaw.
So how do you guard against that?
Strict thresholding helps, like we said. But also, continuous validation is non-negotiable. You need an entirely separate, clean validation set, human-labeled, that you never use for training or pseudo-labeling, only for checking the model's actual performance after each cycle. That's how you catch if it's gone off the rails.
Okay, makes sense. What's the next SSL method?
Method 2 is quite different. It's unsupervised pre-processing, often implemented using something called an autoencoder. This technique kind of sidesteps the labeling issue, at least initially, by focusing purely on feature extraction before the main supervised training even begins.
Feature extraction, like finding the important patterns.
Exactly. A model needs to efficiently understand the fundamental building blocks of the data, the essential features like edges, shapes, textures, to classify things effectively later on. An autoencoder is designed specifically for this, usually through dimensionality reduction.
Dimensionality reduction,
Yeah.
making the data smaller but keeping the essence.
That's a great way to put it. An autoencoder typically has two parts, an encoder and a decoder.
Okay, how does the encoder part work?
The encoder takes the high-dimensional input data, let's say a big 1,000 by 1,000 pixel image, and compresses it down, forces it into a tiny, highly efficient numerical representation. This compressed representation is often called the latent space.
So it squeezes the big image into a small code.
Right. Then the second part, the decoder, takes that tiny code from the latent space and attempts to reconstruct the original 1,000 by 1,000 pixel image from it.
So the model is forced to learn how to represent a huge amount of information
Yeah.
in a really compact way, and then accurately expand it back out again.
Yes. And the only way it can successfully reconstruct the original image with reasonable fidelity is if that tiny latent space representation captured only the truly essential features. It has to learn to discard the noise, the redundant information, the unimportant peripheral context.
I see.
So these condensed, meaningful features learned entirely from the abundant unlabeled data during this pre-processing step become the new, optimized input for the final supervised classification model.
Okay, so in this step, the model isn't learning what a cat is yet. It's learning what an image is, fundamentally, the core structures.
Exactly. It's learning a better representation of the input space.
And by starting the supervised part of the training, with the few expensive labels, using those pre-learned, compressed, meaningful features instead of raw pixels.
The subsequent supervised training becomes vastly more efficient, and the resulting model tends to generalize much better, even with scarce labels, because it started with a richer, cleaner understanding of the input patterns.
Clever. Okay, method 3.
The third approach involves clustering-based methods. These rely on a core assumption, sometimes called the smoothness assumption or the cluster assumption.
Okay, what's the assumption?
It's pretty intuitive, actually. The assumption is simply that data points which are similar in feature space, meaning they are physically close to each other when you visualize them numerically, are likely to belong to the same class. Things that look alike probably are alike.
Makes sense.
So a clustering algorithm, maybe something like k-means, is used to group all the data points together, both the labeled ones and the vastly more numerous unlabeled ones, based purely on their similarity in that feature space. It creates natural groupings or clusters.
Right, so if you get a dense cluster of, say, 50 data points all close together, and you happen to know that maybe 3 points right in the middle of that cluster were manually labeled as cat,
Then the assumption kicks in. You assume that all or most of the other 47 unlabeled points tightly surrounding them within that same cluster are also cat.
and you assign them that pseudo-label.
Precisely. The unlabeled data points within a well-defined, tight cluster inherit the label from their labeled neighbors within that cluster. This technique can be incredibly fast and effective for imposing some initial structure onto large, messy, unlabeled data sets.
But what are the weaknesses? Where can it go wrong?
Its main vulnerability is when those natural clusters aren't very distinct. If clusters overlap significantly, or if the chosen similarity measure, how you define close, fails to capture the subtle nuances that are actually essential for correct classification, then the pseudo-labels assigned can be wrong.
Got it. Okay, that's 3. What's the 4th SSL technique?
The fourth one is interesting because it brings the human expert back into the loop, but in a much smarter, more targeted way than just labeling everything. It's called active learning.
Active learning sounds dynamic.
It is. Active learning is all about maximizing the return on investment, the ROI, for that expensive human labeling effort. It kind of reverses the standard approach instead of the data scientist just randomly picking data points to label.
The model itself asks for help.
In a way, yes. The model performs identification. It flags specific samples from the unlabeled pool where its own prediction confidence is lowest. These are the ambiguous cases, the ones near the decision boundary where it's really unsure.
Ah, the tough calls. The ones where, if labeled correctly, the model would learn the most about where that boundary actually lies.
Absolutely. These are the high-value targets for learning. These low-confidence samples, the ones where the prediction probability might be hovering around 50-50, or maybe samples located right on the existing decision hyperplane. The model has learned so far, those specific samples are routed for intervention.
Intervention meaning?
Meaning they get sent to the human experts for manual labeling.
Okay, so instead of wasting precious expert time labeling 100 super obvious clear-cut images of a dog in perfect lighting,
Right.
the expert only spends their time labeling, say, the 10 blurry, poorly lit, ambiguous images where the model is really struggling to decide if it's a dog or maybe a coyote or even a fox.
That's exactly the idea. It ensures that scarce human expertise and time are concentrated precisely where the model has the greatest need to learn, to resolve ambiguity, and to correct its internal biases or boundary issues.
Which radically boosts the overall efficiency and the model's final generalization capability, but with minimal additional labeling costs compared to labeling everything.
Precisely. And it's often this synergy using unsupervised methods like autoencoders for initial feature learning, maybe pseudo-labeling for broad coverage, clustering for structure, and then active learning for targeted refinement that allows AI to scale effectively beyond the huge limitations of purely supervised, resource-intensive data collection.
Wow. Okay, that's a powerful toolkit for dealing with data scarcity. So we've covered the data foundation, that's ground truth.
Check.
And we've covered the smart data strategy for dealing with scarcity, that's SSL.
Check.
Now we need to get into the engine room, the actual mathematics that provides the feedback signal and drives the whole iterative process of learning. We need to talk about loss functions.
Absolutely. If ground truth is the ultimate goal, the destination, then the loss function is the GPS navigation system. It's the quantifiable scorekeeper and the guide.
Quantifiable scorekeeper.
It's the fundamental tool that measures the model's error. We call that error the loss by calculating the difference between what the model predicted and what the immutable ground truth actually is.
Okay, so going back to that bridge example, if we're predicting the structural stress tolerance,
Right.
and the model predicts it can handle 50 tons, but the ground truth, the actual engineering spec, says it can only handle 45 tons.
Then there's a 5-ton deviation. The loss function takes that 5-ton error and converts it into a single numerical value, the loss score. And that score is something the optimization algorithm can read and act upon.
That numerical score, that quantification, is critical then.
It's the absolute bedrock of machine learning optimization. The loss function mathematically defines, at any given moment, how well or how poorly the model is doing. And crucially, the magnitude of that loss score determines both the necessity and the extent of the parameter adjustments the model needs to make.
So a bigger error means a bigger adjustment needed.
Generally, yes. Training is, from a mathematical perspective, just this continuous process of adjusting the model's internal parameters, its weights and biases, over and over again, always trying to decrease that loss value until it gets minimized below some predefined acceptable threshold.
The error has to be measurable, quantifiable for that learning loop to even exist. You can't improve what you can't measure.
You absolutely can't. And the choice of which loss function to use isn't arbitrary at all. It depends entirely on the type of problem you're trying to solve, because different kinds of problems require fundamentally different ways of measuring error.
Okay, so how do we categorize them? What are the main types?
Broadly, we categorize them into two main families. First, you have regression loss functions. These deal with predictions of continuous values.
Continuous values, like numbers that can be anything within a range.
Exactly. We're talking about predicting things like fluid dynamics, maybe stock prices, house prices, daily temperatures. The prediction is a number on a continuous scale. So the loss function doesn't just need to know if the prediction was close. It needs to measure how far off it was, the exact numerical deviation from the continuous ground truth target value.
Okay, that's regression. What's the other family?
The second family is classification loss functions. These are for predicting categorical or discrete values.
Discrete, meaning distinct categories like labels.
Precisely. Classification involves predicting distinct categories. Is this email spam or not spam? Does this patient have disease A, disease B, or are they healthy? Which species does this plant belong to? Here, the loss function measures something slightly different. It measures how well the model's predicted probabilities for each category align with the single, certain, discrete category provided by the ground truth.
So it's less about how far off numerically
Yeah.
and more about how confident was the model in the right category.
That's a very good way to think about it. It measures the quality of the model's confidence in its categorical assignment.
All right, let's get specific. Let's dive into some actual functions, starting with regression. You mentioned these measure how far off the prediction is. And it seems the big debate here often revolves around how harshly we want to punish errors, especially those big outlier errors.
That's often the key difference, yes.
Which brings us to two really common ones: mean squared error, MSE, versus mean absolute error, MAE.
Right. Let's take mean squared error, MSE, first. It's calculated exactly like it sounds.
Yeah.
You take the difference between the model's prediction and the true ground truth value, you square that difference, and then you average those squared differences across your entire data set. The squaring is the key mechanism here.
Okay, why does squaring the error matter so much? What effect does that have?
Squaring the errors means that large deviations, outliers, get punished disproportionately heavily. Think about it. If your model is off by 1 unit, 1 squared is 1. The loss contribution is 1.
Okay.
But if your model is off by 10 units, 10 squared is 100. The loss contribution is 100. That 10-unit error contributes 100 times more to the total loss than the 1-unit error did.
Wow. Okay, so MSE is highly sensitive to outliers.
Extremely sensitive. You typically choose MSE when stability and safety are absolutely paramount, when even a few massive errors are unacceptable and must be severely penalized. Think about physical simulations, maybe, or certain types of financial modeling where large deviations aren't just noise, they're inherently dangerous or indicate a fundamental model failure.
So MSE forces the model to really prioritize getting those difficult, way off edge cases right, even if doing so maybe sacrifices a tiny bit of accuracy on the majority of the easy, close to correct cases.
That's often the trade-off, yes. It pulls the model strongly towards minimizing those large errors.
Okay, so what's the alternative?
I mean, absolute error, MAE.
MAE is simpler in a way. It measures the average of the absolute differences between prediction and truth. meaning you take the difference, ignore the sign, make it positive, and average those. Crucially, the errors are not squared.
And how does that change the model's behavior compared to MSE?
Well, since the errors aren't squared, large deviations are punished linearly, not exponentially. If you're off by 1 unit, the loss contribution is 1. If you're off by 10 units, the loss contribution is just 10.
Ah, much less dramatic than the 100 we saw with MSE. Much less dramatic. This makes MAE significantly less sensitive, or you could say more robust against outliers compared to MSE. You choose MAE when you know your data inherently contains some noise, or maybe occasional legitimate anomalies like unexpected sensor reading spikes or sudden unpredictable peaks in revenue, which you don't want to overly influence the model's core learning path.
So MAE lets the model kind of find a stable central path through the bulk of the data without getting yanked around violently by those rare, potentially legitimate outlier points.
Exactly. It focuses more on the median tendency, whereas MSE focuses more on the mean, which is heavily influenced by extremes.
That distinction feels really crucial for anyone choosing a loss function. MSE for stability and strongly punishing deviation. MAE for robustness against noise and outliers.
It's a fundamental choice based on your data and your goals.
But what if you kind of want both? A bit of stability and a bit of robustness.
Well, that brings us neatly to the strategic compromise, Huber loss.
Huber loss, okay.
Huber loss uses a clever hybrid approach. It's controlled by a parameter usually called delta. For errors that fall below this delta threshold, meaning small, common errors, it behaves exactly like MSE. It squares them.
So it leverages that squaring mechanism, that stability focus, for the small, everyday errors near the target.
Precisely. But, and here's the clever part, for errors that exceed that delta threshold, the big errors, the outliers, Huber loss automatically switches its behavior. It stops squaring and starts acting like MAE, penalizing those large outliers only linearly.
Interesting. So it provides the benefits of MSE's precision close to the target, while also protecting the training process from being completely hijacked by a few extreme outlier points.
Exactly. It offers a more balanced punishment mechanism, robust, yet still precise where it matters most. It's a very popular choice when you suspect outliers, but still care a lot about accuracy near the mean.
Okay, that covers regression loss. Let's switch gears now to classification, where you said we're measuring uncertainty or confidence. The most common loss function here, you hear it everywhere, is cross-entropy loss.
It is indeed omnipresent, especially in neural networks for classification. The foundational concept to grasp here is entropy. In information theory, entropy is basically a measure of uncertainty or surprise or disorder in a system or a probability distribution.
Okay, uncertainty. How does that apply to classification?
Well, think about our ground truth label. When we have a label say the image is definitively spam, we are 100% certain about that fact. There's no uncertainty. So the entropy of the ground truth itself is effectively zero.
Right, reality is certain.
Exactly. Cross-entropy loss then measures the difference or the distance between the model's predicted probability distribution, which usually has some uncertainty, and that absolute certainty of the ground truth reality. It quantifies how much extra uncertainty or information is in the model's prediction compared to the zero uncertainty of the truth.
Okay, let me try to rephrase. If the ground truth says an image is definitely dog, 100% probability on dog, 0% on cat.
Yep.
But the model outputs a prediction that's maybe 51% dog and 49% cat. Even though the model technically got the label right, it picked dog.
The cross-entropy loss would still be quite high.
Yes, is that right?
That's absolutely right. It would be high because the model lacked confidence. It was very uncertain. Cross-entropy heavily punishes the model when it assigns high confidence to the wrong class, and it also penalizes the model, though maybe less severely, when it assigns low confidence to the right class.
So it's driving the model not just to be correct in its final choice, but to push its probability scores towards 100% certainty, or 1.0, for the correct label, and 0%, or 0.0, for all the incorrect labels.
That's precisely its effect. It encourages confident, correct predictions.
Okay. What's another common classification loss? You mentioned hinge loss.
Yes, hinge loss is another important one, particularly used in binary classification problems, and it's often associated with algorithms like support vector machines or SVMs.
How is it different from cross-entropy?
Hinge loss has a fundamentally different goal. Its primary objective isn't just accurate prediction, it's margin maximization.
Margin maximization.
It pushes the model to find a decision boundary that creates the clearest, widest possible separation, a margin between the different categories. It's not enough for a point to be on the correct side of the boundary. Hinge loss encourages the model to place the boundary so that the correctly classified points are as far away from that boundary as possible.
So it wants the model to be not just correct, but confidently correct, with a specified safety distance or buffer zone.
Exactly. That margin provides robustness. It makes the classification decision less sensitive to small variations in the input data, which is crucial in systems where misclassification errors have high costs or consequences.
Okay, fascinating. So we have the loss function calculating the error score, but how does that score actually lead to the model learning or adjusting itself?
That's the final crucial piece. Integrating this measurement back into the learning process. The loss function provides the value, the score, but gradient descent, or one of its many variants, is the algorithm that provides the direction for improvement.
Okay, gradient descent.
The loss value calculated by the loss function is the direct input for these optimization algorithms. You can imagine the loss function plotted out across all possible model parameter settings. It creates a kind of high-dimensional landscape, maybe with hills and valleys.
Right, a loss landscape.
And the model's goal is to find the lowest point in that landscape, the deepest valley floor, which corresponds to the minimum possible loss, the minimum error.
Okay.
Gradient descent works by calculating the gradient at the model's current position on that landscape. The gradient is essentially the slope of the terrain at that point, measured relative to every single adjustable parameter, all the weights and biases in the network.
So the gradient tells the model, okay, if you're standing right here on this slope, the absolute steepest way downhill is exactly, say, 2.5 degrees in this specific direction across all your parameter dimensions.
That's a perfect analogy. The gradient shows the precise direction and magnitude that each parameter must be adjusted in order to descend that gradient most effectively and move towards that valley floor, thereby minimizing the loss score.
And the model just takes a small step in that direction.
Exactly. The model learns iteratively. It calculates the loss, calculates the gradient, takes a small step downhill, recalculates the loss, recalculates the gradient, takes another small step over and over again.
And the size of that step is important too, right?
Critically important. That step size is known as the learning rate. If the learning rate is too large, the model might overshoot the valley floor and bounce around erratically, maybe never settling down.
Or even go uphill again.
Or even diverge completely, yes. But if the learning rate is too small, the model takes tiny, tiny steps and might take an impractically long time to train, or I might get stuck in a small local dip, a local minimum, instead of finding the true lowest point, the global minimum.
Finding the right learning rate is a whole art in itself then.
It absolutely is. But this entire iterative process, measure the error with the loss function, find the direction of improvement with gradient descent, take a step using the learning rate, this is the fundamental engine of how supervised and semi-supervised AI models actually learn from data. #outro.
Okay, let's try and bring this powerful knowledge cycle all together now. We started with ground truth.
The indispensable, often high-cost standard of correctness, the foundation,
Then we moved to semi-supervised learning.
which is the smart, strategic maneuver to overcome those massive resource barriers of labeling. It's what allows models to generalize effectively from limited truth and prevents that disastrous overfitting.
Right. And finally, loss functions.
They're the mathematical navigation tools. They provide that essential, quantifiable feedback loop. They measure the error, convert that error into a penalty score,
And then use gradient descent to translate that score into precise adjustments, guiding the model's internal parameters iteratively until that error is minimized.
Exactly. So hopefully you listening now understand not just what supervised learning achieves, but how truly reliable generalized models are actually architected using these efficient data strategies combined with precise mathematical feedback.
Yeah, this mechanical understanding really gives you, the listener, the ability to critically evaluate any AI system you encounter based on how it was trained, not just what it claims to do. But it also leaves us with, I think, one really provocative final thought, and it loops right back to the beginning, back to ground truth.
Okay.
If the quality, the reliability, the certainty of the ground truth dictates the absolute performance ceiling of any AI model, what happens when the ground truth itself isn't solid? What happens when it's inherently fluid or subjective or maybe highly contested?
Like in areas we discuss complex legal interpretations, maybe predicting geopolitical stability, even some aspects of medical diagnosis or sentiment analysis.
Exactly. When the very foundation, the objective reality we're trying to teach the model, is itself ambiguous or debatable.
Well, then the model's reliability is inherently capped from the start, isn't it? Its predictions will inevitably reflect that underlying uncertainty or ambiguity in the foundation.
Which raises a really essential question, I think, for system designers, but also for us as users of these systems. If we know the ground truth for a particular complex task is maybe only 80% reliable or constantly shifting,
What kind of explicit margin of error should we be building into and frankly communicating about the resulting AI system? And maybe more profoundly, at what point should we simply refuse to automate a decision if the underlying truth remains fundamentally debatable or subjective?
something to chew on till our next deep dive.